Yusuke from Yale is going to tell us about algorithm as experiment. You got 15 minutes. I'll try and give you a 2-minute and a 1-minute warning. Take it away.
Great. So thanks a lot for having me. So today I'm going to talk about algorithm as experiment. So this is an econometric or statistical method project inspired by a variety of applied domains in the subtitle. So this is a joint work with Kohei Yata, who is a job market candidate in econometrics at my home institution, Yale's economics department. The motivation for this project is very simple. So needless to explain to this crowd, but now it's sort of the golden age of decision-making algorithms, right? There is algorithms in machine learning and market design and many other domains are now creating a growing fraction of treatment decisions and recommendations. The goal of this project is to take a specific econometric or causal inference book at the surge of algorithmic resource allocation and decision-making. That is, we are going to claim that these algorithmic treatment decisions and recommendations produce very high quality natural experiments or instrumental variables that are used for doing causal inference and impact evaluation. That is, we are going to claim that algorithm is a natural experiment in a very broad and general sense. Now, why is it the case that algorithm is a natural experiment? So let me start with very high level intuition. So imagine that some algorithm is running to make some final decision or recommendation, which I denote by Z. And this algorithm makes this decision Z based on a bunch of input variables, which I denote by X. Then by definition or by construction, nothing else will directly influence this final decision Z other than these input variables, right? Because any computational algorithm is defined to use only a pre-specified set of input variables. Therefore, conditional on X, focusing on individuals or situations with similar values of X, this algorithm output Z is going to be independent from anything else. As a result, this algorithmic decision Z works as a good instrumental variable for whatever treatment which we are interested in at the end of the day. In other words, this algorithm output Z satisfies the key conditional independence requirement. The agenda of this project is to formalize and operationalize this intuition, okay, as a widely applicable estimator of treatment effects. So we are going to start with an identification analysis where we exactly characterize what causal effects we can identify when we have data coming from a data generating algorithm. And we provide this identification analysis for a big class of algorithms containing both stochastic and deterministic algorithms. And this analysis clarifies that the data from almost every algorithm allows us to identify some causal effect. Then in the main theoretical part, we transform this identification analysis into a practical treatment effect estimator. And we formally prove that our proposed estimator is consistent and asymptotically normal for a well-defined causal effects, even if there are lots of heterogeneities in treatment effects. And this treatment effect estimator is also very easy to implement, even if the input variable vector X is high dimensional and contains lots of elements, and even if the decision-making algorithm is very complex. So even if the decision-making algorithm contains some crazy component, say deep learning, the final treatment effect estimator remains very simple. A key special case of our proposed estimator is a high-dimensional extension of the regression discontinuity design, or RDD. That in the previous framework, imagine that the vector X contains a bunch of running variables that jointly determine treatment assignment or recommendation. Then the previous framework clearly contains a multi-dimensional regression discontinuity design with any number of running variables, right? So we effectively provide a consistent and asymptotically normal estimator that can be applied to such a high-dimensional RDD. In terms of applications and examples, there are lots of potential applications of our framework. So one big group of potential applications is coming from decision-making based on machine learning algorithms. So we may use some simple supervised machine learning or more sophisticated bandit and reinforcement learning type dynamic optimization algorithms. So no matter what specific algorithm is used, the resulting data coming from machine learning algorithms provides examples of our framework. on top of that, there are many social and economic applications as well. Say, think about centralized mechanism design algorithms, auctions, and matching algorithms. These are some sort of complicated examples of decision-making algorithms that transform observable data like bit as bits into the final decision-making about who gets what at what prices, right? So therefore, such mechanism design algorithms are also examples of our framework. Finally, public policy eligibility rules are the final category of our primary examples. Say in Medicaid and bankruptcy laws, whether each of us is eligible for that policy or not is often determined by some algorithmic rule based on observable characteristics like our income level and the family composition and so on. Then such public policy eligibility rules are also examples of decision-making algorithms so that they provide examples of our framework. Then in the spirit of this final category of policy eligibility rules, we provide an original application of our method to evaluate hospital relief funding distributed by the US government during the COVID-19 pandemic. So this framework or this policy domain used some algorithmic rule to determine whether each hospital is eligible for funding or not. So we apply our method to data from this policy to evaluate whether hospital funding had any impacts on hospital activities related to COVID-19. And our empirical bottom line is that this funding policy appeared to have no impacts on any hospital activity whatsoever related to COVID-19. Then here is the theoretical framework. Okay, imagine that there are a bunch of individuals I, and each individual I has a vector of fixed covariates xi, which contains p elements. Then each person first receives some binary treatment recommendation denoted by zi. The most critical assumption is that this binary treatment recommendation zi is assumed to be made by some known algorithm, which I denote by a. And this a is a function from each covariate value into some number in the unit interval. The interpretation is that the output of this function is the conditional probability of a treatment recommendation for individuals with certain covariate values. Okay. Then note that this algorithm may be deterministic in the sense that the output of this algorithm may be either 1 or 0. Then after this treatment recommendation, each person gets the final treatment assignment, which I denote by D. And based on this treatment assignment, each person will finally generate the observed outcome, which I denote by YI. So this is a very standard instrumental variable framework with the additional colored highlighted twist that the treatment recommendation or the instrumental variable Z is made by some known algorithm. Then the key property or assumption about this framework is this conditional independence property. That is, whether each person gets the treatment recommendation Z or not depends only on observable characteristics contained in X. So conditional on X, the treatment recommendation Z needs to be independent from anything else, especially potential outcomes and the potential treatment assignments in brackets. And note that this is often a true property or fact guaranteed by the construction of the algorithm. So this is closer to some underlying property than a real assumption. So our goal is to make, provide some treatment effect estimator in this environment. But to make sure that everybody is on the same page, let me provide a few familiar special cases to understand what this framework is about. So one of the simplest special case of this framework is probably stratified RCT or the propensity score scenario, I think. That is, imagine that the treatment recommendation probability A of X is always strictly between 0 and 1, so that it's stochastic. Then this is just a stratified experiment, stratified on observable characteristics X, and we know what we should do in this setup. But our framework also contains fundamentally different scenarios as well. Imagine that this input vector X contains just a scalar running variable. And conditional on any value of X, the treatment recommendation probability A of X is degenerate, so that's 0 or 1. But as we move across different values of the running variable, there are certain jumps or discontinuities in the treatment recommendation probability. This is the typical regression discontinuity design or RDD scenario, which is also a special case of our framework. So our framework is really an integration of the classic propensity score scenario and the RDD scenario. And this integration allows us to contain many other interesting scenarios like machine learning and market design and high dimensional RDD setups. And for this general setup, there is no standard estimator available. So our goal is to provide an easy to use treatment effect estimator that can be used in any special case of this framework. And here is our proposal. So if you are an empirical researcher, this slide is the only thing you need to remember from this project. So our question is how to use a data set coming from the previous setup to estimate the causal effect of the endogenous treatment D on the final outcome Y. And our proposal is the following two-step estimator. The first step is simple brute force simulation. So let's first fix a small bandwidth delta as well as a large number S of simulations. And given these numbers, let's first simulate X star 1 to X star S. And these are independent draws from the uniform distribution over the delta ball around each individual i's covariate point. That is, in the covariate space, each individual I has a certain covariate point, right? Then around it, let's think about a small neighborhood, okay? Then we span some uniform distribution over that neighborhood, and we draw a bunch of simulation draws from that uniform distribution. Then let's substitute each simulation draw into function A to compute the associated treatment recommendation probability. Finally, we are going to take the empirical average over S simulation draws to compute this blue object, P of X delta. So this P of X delta, okay, is the approximate treatment recommendation probability, okay, averaged over a small neighborhood around each individual i's covariate. Then the second step simply combines the first step simulated blue object with the standard two-stage least square instrumental variable regression. That is, at the end of the day, we are interested in how the outcome Y is influenced by treatment D. But since D is not randomly assigned, we need to instrument for this treatment D by some instrumental variable Z. And our preferred instrument Z is the output of the algorithm. Then to make this instrument a good instrumental variable quasi-randomly assigned, we propose to linearly control for the blue object coming from the first step simulation. And our main result is that this beta coefficient coming from this two-step estimator is consistent and asymptotically normal for a well-defined causal effect. So therefore, this simple two-step estimator is a good enough estimator when we'd like to estimate a treatment effect based on some data coming from any decision-making algorithm, either deterministic or stochastic. Then as an empirical application, we apply our method to evaluate the impact of the so-called CARES Act, that is Coronavirus Aid, Relief, and Economic Security Act. And this is probably by far the largest economic stimulus package ever done over the US history, at least since the World War II. And this act distributed hundreds of billions of dollars in relief funding to struggling hospitals during the COVID-19 pandemic. And the concern was that financially insecure hospitals may be less capable of investing in COVID-19 response efforts. Then we use our method to answer the question of whether this concern was alleviated by this massive amount of funding or not. Then we utilize the institutional feature that this act distributed funding according to some algorithmic rule, and we estimate the amount of funding on hospital activities related to COVID-19 patients. And the bottom line is something like this. If we simply naively use some OLS regression or uncontrolled IV regression, then we tend to find substantially positive and statistically significant quote-unquote effects of funding on the number of COVID-19 patients hospitalized by each hospital. But once we introduce the control for that blue object, which I explained, okay, our method reveals that the previous effects of funding was entirely due to selection bias. And this hospital funding didn't have any causal impact on the number of COVID-19 patients hospitalized by each hospital. So our method sort of reveals the concern that the previous hospital funding regime was not well designed. So the bottom line is that as algorithmic decision-making is the world becomes a mountain of natural experiments and instrumental variables. Then to utilize such algorithm-produced experiments, a general approach is our proposal that is a simple two-stage least square regression with the additional control for the so-called approximate propensity score, which can be implemented by simple simulation. But that's it for now, and thank you so much for your time and attention.